Hi everybody, Dr. Pingle here with a lesson on calculating and visualizing terrain models. This is going to be part one of a several part series on visualizations and data sources. So the history of terrain cartography is very old. So humans interact with terrain. It's one of the most important variables that go into human activity. Sometimes in the Midwest or in cities, we don't really notice terrain. But for many people who are traveling over distances, terrain is a very important part. And so it formed an early part of the basis for many kinds of the earliest maps. So we've got some of the kind of very early ones pictured here. So one of the most famous is Çatalhöyük in Turkey, about 9,000 years old. Some of these dates, by the way, are very uncertain. A lot of big guesses here. We've got the Gosser clay tablet from 2300 BCE. And then a map of Pavlov on a mammoth tusk that's as old as 25,000 BCE. And what you'll see is kind of common to all of these is an inclusion of terrain. So you can definitely see mountains. You can see things like the volcano in the Çatalhöyük map. And so there's plenty of evidence to suggest that human beings included things like hills, mountains, volcanoes, in addition to things like settlements and rivers on the maps that they used. One of the earliest ways to show terrain on a map is a profile drawing. So this is just sort of a side view of a hill drawn on what would otherwise be an orthographic or top-down map. And this is very common because this is the way that human beings experience the terrain. When you look at a mountain, when you look at a hill, it looks something like this, and so they aren't always, always well tied to places. Some better than others, but they kind of evoke this sort of, human perception of mountains. Very often they would include things like shading. So you can see this exhibited in the 1639 map of Hispaniola, part of it here, and this kind of representation, because it's so attractive to humans. Children often, if they want to draw maps, will draw hills this way. So this kind of map technique has persisted. One of my favorite maps is J.R.R. Tolkien's maps of Middle Earth. And so this one comes from The Hobbit that you see at the lower right, the Lonely Mountain. This kind of a technique really does still get used. Probably the most perfect manifestation of that form is in Erwin Rice's maps. So we produced a number of these. This is an example of the 1954 landforms of the United States. This map is actually up in the second floor in one of the classrooms in Davis Hall. So if you get a chance, stop by and take a look. It's a really amazing way to visualize the terrain of the United States. And it's stylized, but it's also highly detailed. So I would encourage you to follow the links and kind of take a look at a high resolution version of this, or stop by and see this in person on the second floor of Davis Hall. Very strongly related to that is this idea of slope shading. So on these kind of profile drawings of hills, they would typically shade one side of it to make it look a little more realistic. And so the idea here is that you're going to borrow from that and you're going to shade the things that are steep. So the darker the color, the steeper the slope. So this is an example of Leonardo da Vinci's map of Tuscany from 1502, showing that where the steep, rugged hills and mountains are shown in this dark brown color. A little more recent than that is Hans Conrad Geiger's shaded relief map of the area around Zurich. So Switzerland is a very mountainous area, and so for that reason, many Swiss cartographers have kind of led the way in terms of mountain cartography. And so this is a way of sort of visualizing the terrain as if you have sort of carved it out and you had it in front of you and you lit it with an artificial light source, and you're just sort of shading it as it would appear. And we're going to see some examples of hill shades used in sort of a modern context, created by artificial means. But this is completely amazing to me because this is done, far before humans ever had the capacity to sort of actually look at this stuff from space. And so this is, taken from rather coarse data, assembled in a very meticulous way, and painted, handcrafted with great care. So this is a really amazing set of maps, actually. Just to remind you, though, that a lot of these techniques sort of overlapped. So again, this is the map of 1639 map of Hispaniola, showing again that hill profile. So many of these different kinds of map techniques are used in an overlapping way. Some map makers would use one technique, some map makers would use another. One of the really interesting techniques that came out was hachures, and so this evolved out of the sort of slope shading technique, but it's a way of sort of increasing or decreasing the spacings, thereby increasing the sort of perception of whether it's darker or not, to indicate slope. So we still have the same sort of pattern: the darker, the steeper. But the darker is not caused by, the darker color. It's caused by a change in either the thickness of the lines or the spacing of the lines, or sometimes both. So closer together, the steeper the slope, the thicker, the steeper the slope. Those kinds of things were done sort of, by hand for a while. Eventually, the system of hachures was standardized based on sort of a visual perceptual system. This was done by an Austrian cartographer, J.G. Lehmann. So what you've got here is a table sort of illustrating what those thicknesses and spacing should look like according to different slope values, where anything above 45 degrees was just shaded a dark black. This is an example of what that would have looked like. So this comes from Edward Imhoff's book, 1965, illustrating this idea of slope hachuring. So you can really see just visually, if I said, pick out the areas that are steep, pick out the areas that are less steep or flat, or relatively flat. None of this is flat. You could do so very easily, right? You just look for the areas that are dark, and you would know exactly where the slopes were the steepest. The direction is also indicating what is uphill. Edward Imhoff is a real giant in the field of cartography, and he was a Swiss cartographer himself, and was just instrumental in sort of cataloging and developing a lot of the techniques that we use today. So if you're interested in this book is actually still available, Cartographic Relief Presentation. It's a true classic in the field. Originally published in the 60s, but is still reprinted by Esri Press today. Of course, probably one of the ways, other than sort of the hill profile that children kind of draw, maybe your first exposure to terrain cartography is contour lines, which is very interesting because contour lines are notoriously difficult for people to pick up. So the idea, of course, is that you're connecting lines of equal elevation, and in doing so, you're creating this sort of system of sort of vaguely parallel lines moving around the landscape, forming these non-overlapping sort of concentric circle-like things as they go up the hill. So if you look at Katy Hill there, you can sort of see the rings of the hill kind of coming off around it. And then they get a little more irregular as the landscape gets a little more varied. So this technique is actually very common. You'll see it on USGS topographic maps, but it is actually fairly difficult for people to understand. One of the ways that's kind of evolved to represent terrain is hypsometric images. And so the idea here is to represent not slope, but elevation with color. And so maybe you've seen something like the image at the right, where you've got sort of a mountain, higher elevations. The highest elevations are shown in white, and then it kind of goes into a brown, and then into green, and then eventually into a blue. This kind of method of mapping elevation to color or gray tone is known as hypsometric tinting. And so while the image at right is the most common, Any convention where you're mapping color to elevation is essentially a hypsometric image. It's very common to use a convention like the higher the lighter, but in many cases you can actually use the inverse. So sometimes the darker the higher is more common. People often use the lighter the higher because of snow, and so that sort of makes sense. But one of the dangers of hypsometric tinting is that people will interpret things incorrectly, and so the image at the lower right there, has white to kind of evoke these snow-capped peaks. But what you're not seeing here is really land cover at all. You're really just seeing elevation, and so people might mistakenly believe that these valleys are green, but of course they may not be. There's really no information about that you can get from just the elevation. So the history of contour mapping is actually very old. So one of the oldest examples of contour mapping is Edmund Halley, the same Halley that's a part of Halley's Comet. And this dates back to 1701. And here you can actually obviously apply these kinds of isolines to anything, right? So contour mapping does not exclusively apply to topography. It can apply to anything. And so one of the earliest uses is actually mapping things like isogonic lines or lines of equal magnetic declination. So lots of variety here. These contour lines were first adapted for nautical charts in 1834 to show depth, but then they rapidly spread to terrestrial use. And so by 1838, you see some common examples of this. And they were standard in British Ordnance Survey maps starting from 1843 onward. And part of the reason for this is that we were able to make these precise measurements over large areas, record things very accurately. And so it became very useful to use maps as recording devices to keep track of these elevations, right? This is before any kind of digital database, and so the map was the repository for this information. There are some very interesting examples of combining contour maps with other techniques. This is an example of computer-generated hachures combined with contours. And so you've got contours expressing this idea of equal elevation. But here we're also using hachures to show where areas are the steepest. And so there's an ability to both extract the metric information, so exactly how high something is, while at the same time retaining this sort of impressionistic view of the environment, where you're seeing the darker areas showing up just very clearly as steeper. Along these lines, there's some really interesting relief techniques that sort of came out of World War II. So this is one of, I think, the most interesting ones. So this is a German Air Force method of conveying information about terrain to pilots, and they used essentially machines to machine out a physical model of the environment, so what we would know as a CNC machine or something like that. And they would drill out essentially this terrain and make a realistic copy of it, and then photograph it, and that would be the way that they would sort of generate something like the hill shaded or shaded relief maps that we saw from Geiger in Switzerland, just created in a slightly different way. So instead of having to sort of imagine these things, they're actually able to create the physical copy of this and then photograph it. The net result would be something that looks like this. So this is a shaded relief or hill shaded map. These are really quite common now. So this is maybe other than contour maps, this is probably the second favorite way that GIS people show terrain on a map. So they generate these hill shades. There are a number of automated techniques that do this. One of the big breakthroughs in computational cartography tracked through the late 60s and into early 80s. Being able to take a digital DEM, so a digital elevation model, a raster of elevation, and to turn that into something that is sort of a good visual representation of what's going on with the terrain. So this technique is really only about, so even though the technique of hill shading dates back to certainly the 60s with Imhoff, and then the 1600s with Geiger, The sort of modern computer-based stuff really is only 40 or 50 years old. One of the really key innovations here is 1991. So Thalen and Pike published the first shaded relief map of the United States. So if you think about what that would have taken in 1991 with computing resources, what they were, this is just a vast amount of elevation data that's contained on this map and then rendered out into a visual image. So this is really the first time that people are able to get a view like this. So certainly we'd had views from space for quite a long time, but it's actually quite difficult to sort of make out terrain features sometimes because, again, land cover can disguise this. So whether something is kind of rocky or craggy or green, the elevation changes don't always show up on maps of space. And so this is really one of my favorite maps. You'll see this around in a number of different places, often forming the base map of another kind of a terrain representation. So it pays to know a little bit more about how these hill shaded maps are created because this is such a dominant form of elevation representation on maps apart from contour lines. It's really, and sometimes even more common than contour lines. It's important to sort of dive in a little bit here and talk about how they're made. So the idea here is you're starting everything with a DEM. So in other words, a rasterized image, usually a rectangular grid. And at each grid center, essentially, at the center of each square, you've got an elevation value. And so the idea here is we want to create a new raster based on those elevation values where we're taking an imaginary light source and we're shining it from a direction, so an azimuth, technically speaking, and we're raising it above the horizon to a certain altitude. So altitude here does not mean like a height, like in meters above the surface. So by default, we imagine the altitude at a angle of 45 degrees off of the horizon. So both of these are defaults. If you run the Hillshade tool in ArcGIS, you'll get sort of this essentially default representation. But you can change these. The other assumption is that if we imagine how much light is coming back, we're going to imagine that it reflects light equally in all directions. So not only does it reflect light equally in all directions, but it also reflects perfectly. So if you sort of shine a light and it hits the surface squarely, let's say, all of the light is essentially going to be reflected back to you. So this is an example kind of pairing those two graphics together. This is an example of what that would look like. On the left is our sort of standard diagram of this. And on the right, we've got a mountainous terrain that we've lit in that way. And so imagine that the light is being shown from the northwest in this representation. So that's an azimuth of 315 degrees. And 45 degrees above the horizon, and you would get an image that looks something like this. This is what that would look like with a simple model. So if we use those exact same settings to shine this imaginary light, we would get something like you see over here at the right. So you'll see the shadows showing up on the lower right side. One of the key things about hill shading, though, is that the appearance of the terrain is highly dependent on those settings. So where the light is coming from is going to make the terrain appear quite different. So this is one version of the terrain kind of lit in a conventional way. And this is that same image shown with the opposite lighting. So I've shown you a little bit about digital elevation models. We've sort of seen the products of these in that we've looked at a hillshade. Let's dive in a little bit and talk about how these elevation values are actually recorded. So a digital elevation model, or DEM, is really the most common way to record elevation data. In general, we would say that this applies to any computational model of terrain, or let's say digital model of terrain. It's almost always surface-based, which means that we're looking at something that's 2.5 dimensional. And the way that we can explain that is it's 3-dimensional, right? It extends into the z direction, but you can't have more than one z value at any given x, y, right? For every x, y, there's only one z, and so that's why it's 2.5 dimensional. In practice, it's almost always square and gridded. Even though we're going to look at some things called triangulated irregular networks, or TINs, as examples of digital elevation storage, most DEMs, and when most people use the term DEMs, they're going to be referring to this rasterized product. Once in a while, you'll see a DEM references a particular storage format for square gridded data. So it would have something like a .dem file extension. That has gotten to be extremely rare. Most of our common storage formats for DEMs are going to be these. So by far the most common is a GeoTIFF. So this is really, so this has a .tif or a .tiff file extension. So this is just in a generic image storage format with a little bit of extra information, metadata, providing things like referencing. So the cool innovation about this technique is that we're taking a digital storage format that was developed for essentially cameras, for images, and using that to store data. So that's a really nice way of doing it, because rather than sort of making geography develop its own storage containers, we can borrow all of the innovations for all of the image data. So a lot of the image processing algorithms and compression are all going to apply to this, and geographers don't have to invent or reinvent the wheel. There are a variety of other storage formats as well. So Esri grid format is extremely common. So you'll see these with a .asc, .txt, or .grd formats. It's increasingly, I would say, getting phased out, although you'll still see it in a number of different places. We'll talk about the sort of details of that. AirDOS Imagine had been quite popular for quite a while. So this is a .img format. This is a really good format. It's just another raster format. It keeps all of its metadata kind of inside the file. It compresses relatively nicely. So there are a lot of advantages to the AirDOS Imagine format. Unfortunately, it seems to be sort of maybe on the decline. Two other data storage formats for elevation rasters are the SDTS-DEM. This has gotten increasingly rare. I haven't seen this out in the wild for quite some time. And this would have a .sdts extension. And then a highly compressed image format called Mr. SID with a .sid format. This was sort of an experimental format. It was doing quite well for a while, but it really never quite turned the corner. So again, Mr. SID format is really starting to disappear, but I wanted to at least mention it so that you've heard of it in case you run across it in the wild. By far, the two most common formats are going to be .tif and an Esri grid format of one kind or another. There are a number of different sources for our elevation data. So one of the greatest sources globally is the Shuttle Radar Topography Mission. So this is actually fairly old data. This was flown back in 2000. The raw data itself was 1 arcsecond, or about 30 meters. Those two things don't go together perfectly. So when we say 1 arcsecond, this is the degrees, minutes, second division. So it would be recorded at every 1 second interval. That breaks down to being about 30 meters, but because lines of longitude converge towards the poles, the x and y direction, even though they are both 1 arcsecond, are different spatially. So the difference between the x direction and the y direction starts to get bigger and bigger as you get towards the pole. However, this SRTM data set was only released to 3 arcseconds globally. Now that doesn't matter so much anymore. Some other data formats or DEM sources, missions, have been flown that have sort of rendered that obsolete. But for a while, it was the case that the National Geospatial Intelligence Agency, or the NGA, didn't want to release areas outside the United States because they wanted to sort of retain an advantage for the United States, as we were the only ones that sort of kept that. And so the full 1 arc second data set was available to the intelligence community and the military, but only to the rest of the world it was only released at 3 arc seconds. Within the United States, the 1 arc second data had been available more or less from the beginning. That SRTM data is, again, sort of the most comprehensive, best data set that we have, not in terms of resolution, but in terms of overall quality. The method of data collection, the fact that it was radar, means that it was able to penetrate through a lot of the sort of atmospheric conditions that can make other methods a little more problematic. And so the SRTM 90-meter data set is actually still quite good. So you can download this stuff through the CGIAR website. There have been a number of different sort of versions of this that have come out. We're on version 4 right now. And they're sort of updating this stuff all the time with ancillary sources. You can download the SRTM data from them directly. One of my favorite interfaces, though, is the SRTM Tile Grabber, which is a fantastic little web map that somebody had ginned up. It just links back. They don't actually host the data. They just kind of link it back to CGIAR. So it's no work for them, really. It's just a really kind of slick interface to disseminate this information. So I highly recommend you pause the video for just a second, Google the SRTM Tile Grabber, and check it out. If you want to download the 30-meter stuff, you can do that for the United States and sort of some of the surrounding areas. So there's a 30-meter SRTM tile downloader. So I would recommend that you take a look at that as well. One of the newest data sources for terrain data, though, is the Aster Global DEM dataset. This is a really nice, complete DEM dataset. It's of higher resolution than has been released globally for the SRTM. This was a mission that was done by NASA in partnership with Japan's space agency. They've essentially done this by using stereo pair images. So the cool thing is that rather than use radar to detect distance, they can use photographs taken that they can essentially put together in the same sort of way that your eyes work. So your eyes basically create two separate images. Your brain compares those two images and uses that to make inferences about the distance away from you. And so this essentially works exactly the same way. The problem with Aster data, though, is that it doesn't work through clouds. So the SRTM data is a little bit more reliable. The good news, though, is that the Aster stuff, eventually they're going to find a couple of frames of an image that are not going to be clouded over. So eventually they sort of have been able to piece this stuff together. It's just taken a little bit of time. This is probably the best global data set that exists right now for elevation. It's available up to 15 meters of resolution. But again, because it's photogrammetrically derived, these clouds lead to what are known as holes in the data. So you can use those SRTM tile grabbers to get a hold of data. However, one of the easiest ways to do it for a particular location in the United States is to download the 1/3 arc second DEM. So this is a 10-meter DEM nominally. So 1 arc second would be 30 meters, so 1/3 arc second is about 10 meters. You can see that we have almost the entire continental US is covered by this 10-meter data set. For data about elevations under the ocean floor, your best data source is the eTopo1 Global Relief Model. So this is a rather coarse elevation model. On land, there are much better data sources. If you're looking for sort of large areas, then this works great. Under the sea, it's important. This is the best data set that we've got globally. So there are other pretty interesting local data sets for this stuff. In fact, one was just released for the area in the Gulf of Mexico, which I would encourage you to take a look at. But globally, this is the best data set that we've got. One of my favorite visualizations of this is the hypsometric curve. So what this is showing you is it's a way of showing how much or what part or percent of the land is at a given elevation. So if you're looking at the right-hand pane of this is showing you the cumulative area. So as it moves, as you move from left to right in the right-hand pane of this, you're getting more and more area accumulating. And so you can sort of, it's this kind of amazing view of how much land there is at each elevation. So you can sort of see Mount Everest over here, very, very, very few peaks reach above that. So anything above 4,000 meters is actually quite rare. And then like extremely rare. Below that, it sort of starts to increase until you get to an elevation of 0. Which is about a third. So, this is saying that about a third of the Earth's surface is above sea level. And then you can sort of look at the distribution below. There's this sort of idea of the continental slope. Very, very little land under the ocean is sort of shallow. It deepens quite quickly, but at not a very steep rate. And then you get down to the oceanic trenches, like the Marianas Trench. Like Mount Everest, these are extremely rare. So there is very little points on the Earth's surface that are below about 6,000 meters. So it's probably worthwhile to talk a little bit about DEMs, DTMs, and DSMs. So there's actually some confusion about the relationship between these three terms. So not everyone is going to use these in the same way. So we'll talk a little bit about the different ways in which they're used, and I'll sort of discuss a little bit about what I think the best way to sort of use them is, knowing that not everybody is really on the same page here. So we've said that DEMs are a digital model of the elevations on the planet. And while this is normally rasters, they can be tins as well. So DTMs are what we would call digital terrain models. And the idea here is that we're representing only the natural surface or bare Earth. The reason that this is important is that as our methods of generating terrain maps or records have gotten better, things that aren't terrain increasingly show up in our data. So things like buildings or trees. Do we want to display a map showing you where the top of the trees are or where the tops of the buildings are? Do we want to imagine that there's a ground surface? Sometimes that's useful. And those maps are called digital surface models. So those are going to include the trees and buildings. So those are DSMs. But many times we want to remove those and get down to what we would think of as the bare Earth. And that bare Earth, with all of the vegetation and all of the buildings stripped off, that's a bit of an artificial construct. But even so, we would refer to that as a digital terrain model. So the best advice that I can give is to try to use DEM as sort of the superset of any kind of elevation record, and to use DTM when you're talking about the bare Earth, and use DSM when you're talking about things that are at the top. So this is a map of the shaded relief or hill shaded image by Thalen and Pike that we saw earlier. This is again sort of a real staple of elevation representation, and so we're going to dive in even a little bit deeper still to learn a little bit more about how these are made. So the idea here is we're going to talk about how much light is going to come back to this imaginary light source. So light projections, we can imagine this light source, even though that's not really how it's done, right? It's done entirely mathematically. But if we imagine the sort of globe and developable surface and imaginary light source, that's kind of what we're getting at here. So imagine this light source, and it's hitting this, and we say 1 is the full amount of light, so 1 is like 100%, right? how much light would get reflected back? Well, under this Lambertian reflector, all of it, right? So all of this light is coming back. But what if the surface is tilted? So we know, or we can imagine that it's going to be less than 1. And the question is, by how much? Well, it turns out that the reflected light, at least under these assumptions, is going to be equal to the cosine of the difference between the sun angle and the ground angle. If we're looking at a slope of 30 degrees, then it's the cosine of 30 degrees, 0.866. So a lot of it, right, is coming back, but not all of it. And of course, as the ground surface gets steeper and steeper, we could imagine that as it gets to a slope of 90 degrees, right, or completely vertical, then none of the light is going to get reflected back, right? It's perpendicular to the sun's rays. This is a graph showing sort of how that falls off as the slope gets steeper. So if 1 is the total amount of light, then you can see that the reflected light sort of diminishes and diminishes and diminishes until you get to 90 degrees. So that's been, I've shown you there sort of a simplification of that approach, just so you can sort of understand it conceptually. The real model is slightly more complex, but it's conceptually similar, right? We're just sort of, instead of the sun being directly overhead, we're going to put the sun at an angle itself. We're still calculating the difference between the sun angle and the angle of the surface. And we're also going to take into account this idea of azimuth. So if it's not directly overhead, it needs to be out of direction, and so we need to specify that as well. The calculation of shaded relief is not all that complex, so this probably looks more difficult than it is, but it's not really much more than sort of multiplications and some simple trigonometric functions. So we're taking the cosines and sines of slopes and zeniths, azimuths, and all of that stuff is fairly straightforward. So you can literally just sort of plug and play this into a Hillshade algorithm. However, the Hillshade is really not all of it. So the Hillshade is another name for the Hillshade is the shaded relief. There are 2 websites kind of put out by not competing, but two different groups of scholars that are very interested in relief representation. So I would encourage you to take a minute, pause the video, and just look up reliefshading.com and shadedrelief.com and poke around those websites a little bit to see a little bit more about them. One of the really interesting ways of representing terrain actually is kind of a refit of the stuff that was done by Imhoff and Geiger. And the idea of this is recreating the sort of Swiss-style relief shading, where we're taking into account things like elevation, but we're also taking into account the sort of traditional shaded relief values. So we're using a gray shaded relief as one part of our input, but we're also using elevation as a second part, right? So we're combining things like hypsometric shading with a gray shaded relief to create this very powerful colored shaded relief image. These kinds of techniques, combining a hypsometric image with hill shading, are really powerful techniques. This is commonly done with a semi-transparent elevation layer. But again, if you've got a moment, I would encourage you to pause the video and take a look at this website. So this is one of the Esri blog posts talking about sort of new ways of representing this combination between a hill shade and elevation values. This idea of sort of combining 2 different representations, we've seen a little of this before, the combination of contour lines and hachures. This is one of my favorites. So this comes from Tanaka. This was done in 1950 from some work, as I understand it, that came out of Japan's military experience during World War II. And the idea here is we're using contours along with sort of something that mimics hill shading. So we draw the contours, but we draw the contours white on the side that's sort of facing our imaginary light source. And we draw the contours black in areas where it's away from the light source. So this is a really powerful way of sort of both, again, showing the absolute value of the elevation, but also creating the sort of impressionistic view. So you can quickly see sort of what's steep and what's not. This is one of my favorite images of Tanaka's method. So this is showing an area in Japan, and the volcanoes just come out beautifully. So this is really the strength of this method. So you can sort of see the terraced-looking hill slopes, especially in the south. What you get with a method like this is essentially a hillshade, but retaining the all of the advantages of a contour map. So we can recover precise elevation values, but it still has this incredible impressionistic way of conveying the terrain. A very similar method is actually a shadowed contouring. While Tanaka's method had sort of a white side and a dark side, this has a thinner line on the lit or the lighted side, and a thicker line on the shadowed side. So it has a very similar kind of an effect. The benefit of this method is I think that it doesn't require a sort of a gray medium tone to kind of exist all across the map. So most of the base of this is white, and then the rest of it is just black. And the real advantage to a method like this is that it's going to more easily lend itself to combining this with other methods. So I like to think of this as sort of one channel of information, the elevation channel, but you might very well want to overlay a second variable on top of this, right? So some other variable that's related to elevation. And so by doing it this way, you can really see, you can really leave that secondary channel of color open for some other thematic variable. There are a couple of great modern adaptations to this. So Pat Kennelly has come up with a couple of enhancements to a traditional hill shaded map, and one of the really great ones is the use of curvature underneath. So this is sort of a combination of using multiple sources of illumination, but also curvature to enhance the sort of carved out nature of many of these slopes. So in this case, a semi-transparent curvature layer is added on. You'll see a little bit more about curvature in the next lesson. So there are other things that you can derive from a DEM. So slope is kind of the most common, but aspect and curvature are two other very common things to carve out of a DEM or to bring out in a DEM. And so this is using that second derivative of elevation. So elevation goes to slope and slope goes to curvature. This is using that curvature to enhance the image. If you're interested in a little bit more about that process, see Aileen Buckley. She's got a nice blog post. It's from 2010. I've got the link here below. So if you just can Google using curvature rasters to enhance terrain representation, there's a really nice article about this if you're interested in sort of implementing it. A couple of other really interesting techniques in visualizing DEMs. One of these comes from Yokoyama. So this is the idea of openness. Openness is sort of this idea of how much sky can you see from any given point on the DEM. So if you can see a lot of sky, that would be a high degree of positive openness. If you can't see very much sky, if you're sort of trapped in a pit or in a ravine, then that would be low on the scale of positive openness. There's actually a couple of different ways of expressing this. So positive and negative openness. Positive openness is how much of the sky can you see. Negative openness is actually the inverse of this. So both of these are very strongly related. The more positive openness, the less negative openness, generally speaking, but not always, right? So they sometimes do differ. Another take on this is Janowitz and Stupinski. So this is deriving classifications of terrain based on the DEM. So they look at the 8 neighbor. They look at 8 neighbors, and actually they're using openness to drive this. So it's not technically speaking the 8 neighbors, but the 8 directions, and describing what are known as geomorphons. So they've got these 10 landform classifications that they use, and this is derivative of some of Wood's work on the subject. A very interesting and powerful way of decomposing the environment. The idea here again is you're looking at 8 directions and figuring out whether you're at sort of the same elevation, whether that neighbor is higher, or whether that neighbor is lower, and using that to drive a classification. You can then color code these for display. So on the upper left is just a standard hillshade, and then some of the other images are showing different representations based on different threshold values for that geomorphon classification, illustrating things like ridges, foot slopes, valleys, pits, and so on. Pat Kennelly is actually really highly involved in this idea of mountain or relief representation. This is one of my favorites of his. So this is a uniform sky illumination model, taking a traditional sort of hillshade and imagining sort of that you're lighting the landscape from not just one point, but from kind of all points simultaneously. And this leads to a really beautiful representation of the terrain. You can apply this to other things as well. In another lecture, we'll be discussing LiDAR. LiDAR is a way of generating really high resolution images from a laser scanner. So these are creating DEMs, DTMs, DSMs at resolutions often of 1 meter per pixel or better. So you can really see things like buildings, walls, things what we would call micro topography. And so Pat Kennelly's method of using this uniform sky illumination is very powerful, really brings out the richness. So at left you see a hill shaded view of a LiDAR, and you can sort of pick out building outlines. Those come out pretty clearly. But comparatively, when you look at the uniform illumination model, the buildings just pop right out. It's quite easy to see. A lot of the basic techniques are going to be available as part of the Spatial Analyst and 3D Analyst toolkits, so look for them there. The ones we talked about today, mostly the hillshade and contours, can both be generated from these toolboxes. Some of the other tools, aspect, slope, curvature, we'll be talking about it in another, viewshed, we'll be talking about it in another lecture. If you're going to use the hillshade, you're going to need to set the Z factor correctly. So this is one of those things you would sort of think that a GIS would be able to fill in on its own. I expect at some point it will. However, at the moment, what you need to do is you need to specify sort of the difference between the units in the X and Y directions and the units in the Z direction. So we said that a typical DEM is going to be recorded at 1 arc second intervals, or maybe if you're downloading it from the national map, maybe 1/3 arc second intervals. But what we're talking about here is degrees, right? So your X and Y unit are fundamentally degrees. And your Z unit is typically going to be something else, and often meters, never degrees. And so you need to specify sort of the difference between your Z unit and your X and Y unit. And that ratio is called the Z factor. So the Z factor is usually quite small. You can see here what we've got is one that's 8.99, but times 10 to the -6. So it's a very, very small metric. Not specifying the Z factor correctly, the tool will run. If you don't specify Z factor, it will assume a Z factor of 1. If you use the wrong one, what you're typically going to do is you're going to make the slopes appear quite steep. So if you generate a hillshade and it doesn't look right, there's a good chance that you need to specify a Z factor or project your data. This is a table of values, sort of typical values for Z factors. It turns out that if you're ballpark close, you're probably going to be fine, at least in terms of a visualization. So there's a blog post that I've linked here on setting the Z factor parameter correctly. You're welcome to sort of copy and paste to these values in. Like I said, ballpark is generally just fine. And what you're looking at here is some very, very small numbers, right? So 0.00000912 for 10 degrees of latitude. Very small numbers. So you would set these according to the hypothetical center of your DEM. So you would sort of figure out where the center is, right? So if your DEM stretches from, this would be a big DEM, but let's say it stretched from 20 degrees to 30 degrees, then you would choose 25 degrees of latitude and use the Z value accordingly. And of course, longitude doesn't matter. Latitude is the only determinant here. There are also some web pages that will do this for you. You're free to Google these when you need them. You can essentially just plug these values in here, and get Z values. In this case, what we're looking for is the number of meters in 1 degree of latitude or longitude, and so you would just divide 1 by 83,061 to get a very close value. Again, if you're just using sort of values in the table, anything ballpark close is fine, but this is how you would figure out the precise value if you wanted it. So I've said that using the Z factor is a way to sort of correct for these errors when your horizontal units are fundamentally in degrees, right? If they're in arc seconds, that's going to be part of a degree. You can set the Z factor and you're going to get something that looks just about right. However, the right way of doing this is really projecting your raster. So in earlier lectures, we've seen project raster as a tool. That's really what you want to do. You want to project your raster to a local coordinate system like UTM or state plane, and then create the hillshade from that. And that's always going to produce the best image. When you do that, then there's no need to specify the Z factor. The Z factor is 1 because now you're using meters in your natively as part of your horizontal unit, and so your vertical units and your horizontal units will match. There are new things going on in visualization of terrain all the time. This is an area actually in which I work pretty often, mostly with LiDAR data. But Esri has been working on, for instance, a new next generation hillshade algorithm. There's a link to the blog post below. And this is essentially using Pat Kennelly's work. So this is a multi-dimensional hillshade. Instead of having this sort of gray tone throughout most of the map, what this does is it helps to brighten up most of it to make that white, and it sort of enhances the contrast, and so you can really start to see the difference between sort of the steep side of a slope, something that's kind of hidden like the ravine that's kind of running through the northwest part of that image, and the rest of it. So it also frees up that color channel, as I said. If you wanted to overlay another variable on top of this, whether it's hypsometric elevations or something else, that image at the right is going to just look a lot cleaner. The colors are going to wash out much less. So avail yourself of these new tools if you can. The hillshade is standard. It's still a good standard, but there are some great new tools out there, and I would encourage you to try to use those if you're making a terrain map. So with that, I will sign off. Thanks very much for taking a look at terrain representation. It's an interesting topic. It's a growing topic. It's a topic that's kind of near and dear to my heart. So I hope you found it as interesting as I do. Practice this stuff and get good at it, and this can really add a lot of value to your maps. So thanks for listening, and we'll catch you next time.